Alright, so this video is just to give you a little bit of a introduction and some examples related to integration with U-Substitution. Since I wasn't in class on Friday to go through these examples with you, this will still give you enough ability to do the homework that was assigned. So let's just go through and do a couple basic examples of U-Substitution. Now, the whole point, as we talked about, some of us on Thursday, of why we need this method, is if you wanted to try to algebraically take this whole integrand and turn it into a polynomial, that's going to be very tedious and very painful to try to do and may lead to some algebraic mistakes. So what we do is we introduce a new variable, call it u. We pick the inside function of a composition. So in this case, I see a composition of x squared minus 9 cubed. So why don't I call u just x squared minus 9? So now this piece becomes u cubed. But we have to figure out how to take care of the 2x dx. And where we get that is we take the derivative of u with implicit differentiation. So if u is 2x or is x squared minus 9, du is 2x dx. And what do you know? How convenient that is. This part now can become just du. So in terms of u's, this function becomes u cubed du. It's the same as integrating that, which I know you all know how to do. That's 1/4 u to the 4th plus c. And then the final step is to just make the answer back in terms of x's. So we get 1/4 x squared minus 9 to the 4th plus c. And if you took the derivative of that, just to verify, I'm not going to do this for all the problems I have today, but if you took the derivative of that to verify that it worked, think about the chain rule. You start with the outer function, which is the 4th power. You would bring it down to multiply by the 1/4, which would just become 1. Then the 4th degree of the outer exponent would drop by a degree to be cubed. But then you'd have to multiply that by the derivative of x squared minus 9, the inner derivative, which is 2x. And what do you know? You do end up getting the original integrand from the integral that's printed at the top of the slide. So it has to work. Let's try another one. So same thing. I couldn't really simplify the cube root of 1 minus 2x squared to multiply it with that minus 4x. Just way too much work. So instead, let's call that inner 1 minus 2x squared, let's call that just the letter u now. So that gives us the cube root of u, but we still have to deal with the minus 4x dx. And you guessed it, if we take the derivative of u, now we get minus 4x dx. And that's exactly what we want. That's going to be u with the du. So using substitution, we get the integral of, I'm going to write it as a fraction, u to the 1/3 du. And we know it's easier to write it as a fraction because then we can take our antiderivative by adding 1 and then dividing by the new power, which is 4/3. So we get 3/4 u to the 4/3 plus c, which equals 3/4 the quantity 1 minus 2x squared plus c. Oh, I forgot the 4/3 power there. Okay, so that's kind of the basic of U-substitution. Now, let's do some other ones. Okay, same idea here. You've got some very complicated functions going on, so it makes sense to take this inside function in this next derivative and call it u. So we'll let u equal x to the 3rd plus 5. Then when we do our differentiation step to get that du, we get 3x squared dx. But now we have a little bit of a problem here. And the problem is, I don't have a 3 inside this integral. I only have an x squared dx. So I've got to use this du equation somehow to get this to be just x squared dx. So here's an idea. Why don't I take the whole equation and multiply it by 1/3 on either side? Now I get 1/3 du equals just x squared dx. And look at that. Now everything is written in terms of just u's. So the integral of x squared times the quantity x cubed plus 5 all to the 4th becomes u to the 4th times 1/3 du. And since this is 1/3 is nothing more than a constant, we can shove it to the left of the integral sign and make this 1/3 the integral of u to the 4th du, which again, antiderivative of that is not that bad. It's 1/5 u to the 5th plus c. The two fractions can now get multiplied together to be 1/15. And we can put our x cubed plus 5 back in for the u. And there is your antiderivative, 1/15 times the quantity x cubed plus 5 to the fifth. Looking now at this bottom example, so we have the integral of x times the quantity 4x squared plus 3 raised to the third dx. So again, we see this composition, a function raised to the third. That inner function is going to always be that candidate for the u. So why don't we call 4x squared plus 3 now just the letter u? And then when we differentiate both sides, we get 8x dx. But I don't want 8x dx because I don't have an 8 in my integrand. So if I take the entire equation and multiply it by 1 over 8, now I get 1/8 du equals just the x dx that I wanted. So that becomes du. The 4x squared minus 3 becomes just u. The 1/8, since it's a constant, we can move in front of the integral sign. So we get 1/8 u cubed du. Again, the antiderivative of this is not so bad. It's 1/4 u to the fourth. Don't forget the plus c. So we can just multiply those two constant fractions, 1 over 32. We can plug the 4x squared plus 3 back in for u, raise it now to the fourth power, plus c. That is my indefinite integral using u sub. All right, here's a couple more. Now these have some radicals going on. Again, think of this like a composition of functions because we're doing t to the fourth plus 5, and then we're taking it to the 1/2 power. So again, t to the fourth plus 5 would make the most sense to be the u. Another reason why it would make sense to be the u is, as you're starting to see now, the next step after defining u is taking the derivative of u. And notice that the derivative of t to the fourth plus 5 looks somewhat like what's left over in the problem. Do we have to do a little bit of fudging again? Yes, but that's why I would choose t to the fourth plus 5 and not t cubed. Because if you use t cubed to be your u, your derivative doesn't help you much. It doesn't help you get other things out of in terms of t and in terms of u. So anyway, we take the derivative of t to the fourth plus 5. We get 4t cubed dt. Again, I don't have a 4, so if I multiply the entire du equation by 1/4, now I get rid of that 4 on the t side, and I get exactly what I want to sub out for t cubed dt. So this becomes 1/4 the integral of the square root of u du, which again in exponential notation is u to the 1/2 du. So we'll add 1, divide by the new fraction or the new power, which is 3 over 2. So I get 1/4 times 2/3 u to the 3 over 2 plus c. I can multiply the fractions, so I get now 1/6. I'll replace u with t to the fourth plus 5 to the 3/2 plus c, and that is my antiderivative. All right, let's do one more. So same pattern. We'll make u, well, in this case, u is a bad choice for a second variable. So why don't we go to x just for the heck of it, okay? We'll call x u cubed plus 2. I'm only doing that because I know it looks like I'm being contradictory, but you don't want to use the same letter to substitute. So we'll pick a different letter. We'll go to x instead of u. So then that means dx is going to equal 3u squared du. All right, well, I have the u squared part, so if I multiply the whole equation by 1/3, now I don't have the 3 with the u's. So this becomes 1/3 the integral of x to the 1/2 dx. Well, the antiderivative of that is the same as the last problem, so we get 1/3 times 2/3, that should be a 2, x to the 3 over 2 plus c, which is going to equal 2 over 9, plugging in u cubed plus 2 back in, u cubed plus 2 raised to the 3/2 plus c. Okay, this should hopefully give you plenty of examples that are similar to what I assigned for homework this weekend, that you can give that a go. We have lots more to say about U-Substitution, which is what we'll be devoting next week to, but this should be enough to at least give you enough background to try the homework. All right, If there's any questions over the weekend, please feel free to email me. Otherwise, I look forward to seeing everybody back in class on Monday. Enjoy the rest of your weekend.